how the Apollo program actually made decisions. Before Apollo existed as hardware, it existed as commitment. The decision to go to the moon came before the tools were ready, before the processes were stable, before anyone could honestly describe how the goal would be achieved. The requirement arrived first. The system followed. That ordering mattered. Early choices were made in an environment where delay carried its own risk. Architectures were selected without full testing. Contractors were assigned before designs were settled. Paths were chosen because they could be executed within the deadline, not because they were proven optimal. Once the commitment was public, reversal became politically impossible. Once funding lines were established, architectures hardened. Once manufacturing began, flexibility narrowed. The program crossed points of no return long before the first crew ever flew. Each decision reduced the number of options available for the next one. Each milestone made earlier assumptions more expensive to revisit. Apollo did not move forward because uncertainty disappeared. It moved forward because stopping would have made uncertainty worse. That commitment took the form of a fixed deadline. The deadline existed before the hardware, before the crews, before many of the answers. It was public, political, and immovable. The date mattered more than elegance, more than optimization, and often more than comfort with risk. By the time Apollo hardware began flying, the program was already operating inside a narrowing corridor. Technology advanced unevenly. Some systems matured quickly, others lagged. Budgets were finite. Manufacturing timelines overlapped with design work. Political expectations were not abstract pressure. They were visible, measurable, and constantly reinforced. The schedule did not wait for certainty. Decisions were made with incomplete information because waiting for complete information was not an option. Many of those decisions carried consequences that could not be undone later. Some were correct. Some were compromises. Others were simply survivable. Apollo moved forward by deciding which problems could be tolerated long enough to reach the next milestone. That approach shaped everything: spacecraft design, mission structure, training, operations. The program did not assume that risk could be eliminated early and managed later. It assumed the opposite. Risk would persist, shift, and resurface. The question was where it would live and who would carry it. Apollo worked because people understood where they still had control and where they did not. They understood that not every weakness could be repaired, not every system could be improved, and not every concern could be resolved before flight. They learned to distinguish between flaws that threatened the program and flaws that could be managed operationally. This was not a philosophy developed after success. It was a working reality from the beginning. Hardware was being built while missions were still being imagined. Crews trained for spacecraft that were still changing. Procedures were written for systems whose final behavior was not yet fully known. The program advanced anyway, not because uncertainty disappeared, but because the organization learned how to move while carrying it. This episode looks at how those decisions were made inside a real program, under pressure, without the benefit of hindsight. Not the story of a perfect machine, the story of a system that learned how to proceed without one. Part 1. What the Apollo program was trying to accomplish. Apollo was tasked with delivering a result within a decade. That constraint shaped the program before a single piece of flight hardware existed. The schedule was not an outcome of the work. It was the condition under which the work happened. There was no allowance for waiting until technology matured, no ability to pause until design stabilized. Planning and execution had to proceed in parallel, even as the underlying systems were still changing. Apollo became a program doing many things at once. Hardware development overlapped with mission design. Procedures were written while systems were still being tested. Astronauts trained for flights whose final configurations were not yet locked. Decisions made early were carried forward because reversing them later would have disrupted too many connected pieces. This created constant tension across the organization. Engineers pushed for margin and refinement. Program managers pushed for progress and integration. Contractors worked on different timelines, often optimizing for their own subsystems rather than the whole vehicle. NASA did not resolve these conflicts by choosing a single priority. It managed them by deciding where flexibility could exist and where it could not. Subsystems matured unevenly. Some designs stabilized early and became anchors for everything else. Others lagged and were forced to adapt around those anchors. Once production began, stability became more valuable than improvement. This was especially visible in the spacecraft itself. The Apollo command module was densely packed and difficult to modify once assembled. Wiring was complex. Access was limited. Internal layouts reflected early decisions made under time pressure, not idealized designs created with full hindsight. Changing those layouts would have required requalifying structures, reanalyzing thermal behavior, and rerunning test programs the schedule could not absorb. Those consequences were understood and deliberately avoided. Instead of redesign, the program shifted the burden elsewhere. Procedures became more detailed. Training became more intense. Mission rules became stricter. The organization absorbed complexity so the hardware could remain stable. This was not a temporary compromise. It became a defining feature of how Apollo operated. The program did not attempt to eliminate uncertainty all at once. It distributed it across time. Each mission validated part of the system while carrying known limitations forward. Risk was not removed before flight. It was managed across a sequence of flights, each one narrowing uncertainty without resetting the program. Apollo did not need to be perfect at any single moment. It needed to remain coherent long enough to reach the next milestone. Losses, delays, and partial failures were expected. What mattered was whether the program could continue without losing momentum or fracturing under its own complexity. Apollo moved forward by structuring itself so uncertainty did not stop progress. That decision shaped everything that followed. Part 2. How Apollo thought about risk. Risk inside the Apollo program was never treated as a single calculation. It was broken apart, debated, categorized, and tracked across time. Different kinds of risk were handled differently, not because of philosophy, but because the program had limited ability to redesign major systems once production began. Some risks were considered unacceptable under any circumstances. They triggered redesign, delay, or mission cancellation. Others were tolerated if they could be bounded, monitored, or compensated for elsewhere in the system. A smaller number were accepted because removing them would have destabilized the program more than carrying them forward. These decisions were not abstract. Risk was evaluated in context, at specific moments, with specific constraints in place. Engineers identified failure modes and estimated likelihoods. Program managers evaluated schedule impact and integration risk. Flight planners considered how failures would unfold over time and whether crews could respond in real conditions. What mattered was not whether a system could fail. It was how it failed. A failure that degraded capability gradually was treated differently from one that failed abruptly. A failure that produced ambiguous signals was more dangerous than one that was immediately obvious. A failure that required rapid crew response carried different implications than one that allowed time for analysis. This led to a layered approach. A system might be risky in isolation, but acceptable when paired with specific procedures, training, or mission rules. Another system might be technically robust but rejected because it introduced operational complexity that could not be reliably managed. Risk decisions were rarely final. They were revisited as data accumulated, but within narrowing bounds. Once hardware entered production, the question shifted from whether a risk could be removed to whether it could be lived with. This is where Apollo's thinking diverged from later interpretations. Risk was not something to be minimized globally, it was something to be distributed intelligently. Some risk was pushed into hardware, some into operations, some into training, some into crew workload. The program constantly negotiated where uncertainty would reside. Automation was limited, not because it was unavailable, but because it was difficult to verify across all possible scenarios. Human judgment was relied upon not because it was flawless, but because it could adapt when systems behaved in unexpected ways. The spacecraft and the organization were designed together. Machines handled what they could do consistently. People handled what required interpretation. Procedures bridged the gap. The question was never whether Apollo carried risk. It was which risks the program chose to carry, how visible those risks were, and whether the organization was prepared to manage them when they surfaced. That way of thinking shaped how missions were flown, how responsibilities were divided, and how decisions were made in real time. Risk was not eliminated. It was understood well enough to proceed. And by the time Apollo hardware was being tested as an integrated system, many of its limitations were already visible. They appeared in test data, in simulation results, in edge cases that behaved slightly outside prediction. Some were documented as concerns. Others were flagged as watch items. A smaller number were understood as weaknesses that would not be corrected before flight. None of this was hidden. Engineering reviews captured the gaps between ideal behavior and actual performance. Margins were thinner than preferred. Certain systems required careful handling. Some components behaved reliably only within narrow operating ranges. The question was no longer whether these issues existed. It was what to do about them. Correcting every limitation would have required reopening designs that were already feeding into manufacturing, testing, and training pipelines. Fixes cascaded. Schedules slipped. New failure modes appeared as old ones were removed. The program learned that improvement was not free. In many cases, the response was documentation rather than redesign. Limitations were written into operating procedures. Constraints were translated into mission rules. Test results became guidance on how systems should be used, not reasons to replace them. Risk was not eliminated. It was formalized. Some weaknesses were accepted because they were predictable. Others were accepted because they could be monitored. A few were accepted because addressing them would have destabilized the entire program. These were not passive decisions. They were debated, reviewed, and carried forward deliberately. Engineers continued to refine understanding even when hardware could no longer change. Operations teams learned where systems became fragile. Training scenarios incorporated known edge cases so crews and controllers would recognize them when they appeared in flight. Living with limitations became part of the program's operating model. The spacecraft was not treated as an abstract design. It was treated as a real machine with specific behaviors that had to be respected. That mindset mattered. It meant that flaws were not surprises waiting to be discovered. They were conditions to be managed. The program did not assume that every weakness would lead to failure. It assumed that failure would occur when weaknesses were misunderstood or ignored. Apollo advanced with open eyes. Known limitations were carried forward not as oversights, but as obligations. Everyone involved understood that these constraints would eventually surface during flight. The task was not to pretend they did not exist. The task was to be ready when they did. Part 3. Design Trade-offs. That locked the program in. Once Apollo hardware entered production, the program's freedom to change direction narrowed sharply. Early in development, designs were fluid. Concepts were debated. Alternatives were explored. But once manufacturing began, those debates closed. Hardware already built carried assumptions that could not be undone without restarting entire chains of work. Changing a single component was never just a single change. It affected structures, mass balance, thermal behavior, power distribution, testing protocols, and crew procedures. A modification that looked minor on paper could force months of requalification and introduce new unknowns late in the schedule. Apollo could not afford that. As a result, the program transitioned from exploration to consolidation. Improvements did not stop, but they slowed. Changes were no longer evaluated primarily on performance gains. They were evaluated on how much disruption they introduced into a system that already existed. This created a structural bias toward stability. Systems that worked well enough were preserved. Designs that were awkward but understood were kept. Known limitations became preferable to unknown improvements. The guidance computer illustrates this logic clearly. It was limited in memory and processing power. Its capabilities were stretched through efficient software rather than expanded hardware. More capable alternatives existed, and some were proposed. Adopting them would have required changes across navigation, crew training, mission procedures, simulations, and verification processes. Those changes would have rippled outward, affecting timelines the program could not move. The existing system was constrained, but it was predictable. Apollo stayed with it and learned how to operate within its limits. This pattern repeated across the spacecraft. Wiring layouts that were difficult to access were left in place. Thermal designs that required careful operational management were accepted. Redundancy was added selectively, not universally, because redundancy itself increased complexity. The spacecraft became a fixed reference point. As hardware flexibility decreased, operational flexibility increased to compensate. Procedures grew longer, mission rules became more detailed, training scenarios expanded, the organization absorbed complexity so the machines could remain stable. This was not an oversight. It was a deliberate exchange. The program understood that it could not optimize everything at once. It chose to optimize for reliability of understanding rather than theoretical performance. By the time Apollo missions approached the Moon, the spacecraft reflected years of decisions that were no longer open for debate. They were settled. What remained was learning how to live inside those decisions. From that point forward, improvement stopped meaning redesign. The spacecraft that would fly was the spacecraft the crews would live with. Its limitations were no longer design questions. They were operational facts. Procedures absorbed what hardware could not change. Training became the place where flaws were confronted rather than corrected. Mission rules hardened around what the spacecraft reliably did, not what it might do under ideal conditions. The burden did not disappear, it moved. The spacecraft stopped evolving. The organization did not. Part 4. When plans met reality. Apollo missions were planned down to the minute. Timelines were dense. Activities were sequenced tightly. Every action had a checklist, and every checklist had contingencies layered beneath it. The structure created the appearance of precision. Flight rarely matched it. Even on nominal missions, systems behaved differently once they left the ground. Temperatures drifted outside predicted ranges. Power consumption varied subtly over time. Sensors disagreed with one another. Signals fluctuated in ways simulations never fully captured. Most deviations were small. The challenge was not eliminating them. It was deciding which ones mattered. Mission Control learned early that not every alarm represented danger. Alarms sounded frequently. Telemetry spiked. Values jumped, dropped, and recovered. The spacecraft produced noise that looked alarming in isolation, but meant little in context. Controllers learned to read patterns instead of individual signals. A single anomalous reading mattered less than how readings interacted over time. Slow trends were more important than sudden spikes. Context mattered more than procedure. This kind of judgment could not be automated. It had to be learned. Simulations were designed to be uncomfortable. Controllers were placed in scenarios that violated expectations. Failures were combined in unfamiliar ways. Information was delayed, distorted, or withheld. Scenarios unfolded without warning and often without clean resolution. The goal was not to test whether procedures were memorized. It was to force teams to operate when procedures no longer fit neatly. When problems emerged in flight, responses followed a disciplined narrowing of focus. What is failing? What is still working? What does the crew need right now? These questions were not rhetorical. They were asked repeatedly, out loud, as data evolved. Some problems allowed time for analysis. Others demanded immediate action. Recognizing the difference mattered more than identifying the failure itself. Treating a slow problem as urgent introduced risk. Treating an urgent problem as analytical wasted time that could not be recovered. Not every issue could be fixed. Some systems were isolated and left degraded. Some failures were tolerated because correcting them would have introduced greater uncertainty elsewhere. Missions were reshaped to preserve primary objectives while abandoning secondary ones. Plans were written with this reality in mind. They were not rigid scripts. They were frameworks designed to survive deviation. Operational discipline allowed missions to continue even when reality diverged sharply from expectation. By the time Apollo crews reached lunar orbit and beyond, the program was no longer relying on design elegance. It was relying on judgment earned through repetition, discomfort, and constraint. Part 5. When failure could not be planned away. Apollo was designed with failure in mind, but only to a point. Certain failures were expected, others were discussed and rehearsed. A smaller number were considered unlikely, but survivable. Then there were failures that forced assumptions to collapse. Apollo 13 was one of them. When the oxygen tank failed, the problem was not a single broken component. Power generation was lost. Life support margins shrank. The command module could no longer support the crew for the remainder of the mission. What mattered immediately was time. Every hour was measured against battery capacity, oxygen availability, carbon dioxide accumulation, and temperature loss. The problem was not how to fix the spacecraft. It was how to keep the crew alive long enough to get home. The response was triage. Systems were evaluated not for elegance, but for survival value. What consumed power? What preserved breathable air? What could be shut down without becoming unrecoverable later? The lunar module became a lifeboat, not because it was designed for that role, but because it could support life independently. There were no clean solutions. Power was shut down at the risk of damaging systems permanently. Navigation was recalculated using unfamiliar techniques. Carbon dioxide buildup became a critical threat because equipment was operating far outside its intended envelope. Every decision traded one risk for another. Solutions came from familiarity rather than innovation. Engineers understood the spacecraft deeply enough to repurpose what already existed. Crews followed procedures that felt wrong in any other context but made sense under the constraints they faced. Work continued inside shrinking margins. There was no moment where the situation became safe. There was only a gradual reduction of uncertainty until recovery became possible. Apollo 13 did not demonstrate that the spacecraft was robust. It demonstrated that the organization was. Afterward, some procedures were revised. Some assumptions were retired. Certain risks were reconsidered. The structure remained intact. The program did not become safer because it eliminated risk. It became safer because it understood where risk actually lived. Part 6. What Apollo reveals about large programs. By the end of Apollo, the moon landings represented a moment when accumulated decisions held together long enough to succeed. The program worked because it acknowledged its constraints rather than trying to escape them. Time was fixed. Technology was incomplete. Resources were finite. People made mistakes. Apollo was built to operate inside those conditions. Decisions focused on producing systems that could be flown, operated, maintained, and recovered repeatedly within a narrow window. Perfection was never the goal. Continuity was. Change was limited. Scope was controlled. Objectives were constantly reordered as new information arrived. Improvements were evaluated not only for what they added, but for what they destabilized. Every gain carried a cost elsewhere. Those costs were not always resolved. Some were simply carried forward. The program moved ahead even when trade-offs remained uncomfortable. Later space programs inherited Apollo's hardware concepts without inheriting its context. Political pressure shifted. Public tolerance for visible risk declined. Timelines became more elastic in some ways and more fragile in others. Apollo belonged to a specific moment, but the way it made decisions did not. Large technical programs still face immovable deadlines, imperfect systems, and uncertainty that cannot be engineered away. They still require people to choose between stability and improvement, between what is ideal and what is survivable. Apollo shows what it looks like when those choices are made explicitly. The program is remembered for where it went. It is more useful to remember how it operated. As a system built by people making decisions under pressure, with incomplete information and little room to recover from major mistakes. The moon landing was the moment those decisions held together. Subscribe to learn how space programs actually worked and how decisions were made when ideal options were not available. Each episode examines one set of constraints and the systems built around them.